All right, friends, welcome back. In this video, I'd like to go ahead and begin Chapter 2 and take a quick look at Section 2.1 in your textbook, which talks all about linear equations in two variables. So let's get started with that. One of the most important things that you need to remember about linear equations is that they can be written in one of three very, very important forms. And the first form that we are going to take a look at here in this video is what you call your slope-intercept form. And this is probably the most famous form. It's the one that a lot of people are able to recite. That's, of course, your famous y equals mx plus b form, okay? The reason we call that slope-intercept form is because just by taking a look at the equation in this form, you can immediately start to tell what is playing the role of your slope and what's starting to play the role of your y-intercept, okay? The interpretation there being, if you look at the number b, that is a point with coordinates 0 as the x-coordinate, but the number b is the y-coordinate, so that's why it's your y-intercept, okay? Again, very, very important equation of a line here. Or I should say the very important form of the equation of a line, because remember there's three important ones that I want us to know. Because this gives you everything that you need. It gives you all the tools that you need to create a nice picture of the graph. And so if we go ahead and move on to some examples, that's exactly what I'd like to do. I'd like to take a look at a couple of examples where we have linear equations and then see about what we would need to do to go ahead and create a quick sketch of them. Okay, so here in this first example, we have here in part A, y is equal to 3x minus 2. And the idea here is that we just need to go through and pinpoint what is playing the role of m, our slope, and then what's playing the role of b, our y-intercept, okay? So really quickly about the slope here. It is a positive 3, but remember that slope is interpreted as a rise over a run. And so I'd like to go ahead and write this as a fraction, a rise of 3 for every 1 unit that I run, okay? We can interpret it that way, or with any slope, you could always interpret it as going in the exact opposite directions as well. So if one interpretation was for every 3 I go up, I go 1 to the right, you could also interpret this as for every 3 I fall, I run 1 to the left. Okay, those would give you the exact same stair pattern. So whatever amount of grid space you have, you might go with one of those interpretations over the other. Okay, and then for this other important number here, the y-intercept, remember that this corresponds to a point with coordinates 0, -2. And so if we had to go through and plot this line, which we will now go ahead and do, we're just going to go ahead and begin by plotting that y-intercept. So we said that that was at 0, 2, and then we said that our slope was 3 over 1. So again, that means for every 1, 2, 3 units I rise, I would want to run 1 to the right, and then that would be where I place my next point. Okay, but we also said that the interpretation could also go the other way, so I can say this as for every 3 units I fall, I run 1 to the left, which makes sense because I wrote that as a -3 and a -1. If you were to do -3 over -1, that would just work out to be a negative over a negative, which makes a positive, which is the exact slope that we wanted. Okay, so that's why we have a couple of different interpretations for the slopes whenever we have them. It's at this point where I'm going to go ahead and get a straight line on the page. I just have this virtual ruler here, so I'm just going to line that up really quick against the points that I've got, and then just strike my pen all the way through. A couple of notes about drawing the lines, right? You'll notice that I drew this all the way through the grid. That's very, very important. And you'll also notice that I put my arrowheads on both ends of the line just to signify that these keep going indefinitely, okay? So definitely things I would like to see you doing whenever you're creating your line pictures, all right? This next example here presents another very, very important form for equations of lines, and that is something that we call, of course, standard form of the equation of a line. Okay, so what you're looking at here is something that looks an awful lot like some number a times x plus some number b times y is equal to some number c. Okay, again, we call this the standard form of the equation of a line. And the reason why we might prefer mx plus b, which is your slope-intercept form, is because, like we said before, mx plus b is going to tell you everything that you need to know to create a quick sketch of the line. It turns out here, though, that standard form also has another couple of uses here, too. So here's the idea, right? In geometry class, you learned that if you want to draw a straight line, all you need is 2 points. Okay, you could line up a straight edge against those 2 points and draw your complete picture of a line. The reason that standard form is pretty handy is because it will give you 2 points automatically if you know what you're looking for, right? And what we're looking for are the intercepts here. So standard form can give you the intercepts pretty darn immediately, because remember how to find intercepts from a previous video. We said that all you need to do is plug in 0 for one of your variables and solve for the other. So let's say I was trying to find my x-intercept here. I would plug in 0 for y, and then I would solve for x. Well, if it's written in standard form, if I were to plug in 0 for y, that would be a 6 times y, and that would be 6 times 0, and that would be just 0 itself. And so what that's going to mean is that whenever you have the equation written in standard form, if you plug in 0 for y, it's like that term is basically just going to disappear momentarily, and it's going to give you the ability to solve this for x. So specifically 5x is equal to 30. I would just divide both sides by 5, and then I would get my x-intercept here is going to be a point with coordinates 5, 0. Okay? So standard form is really handy for being able to do this, and likewise, we can also use this to go ahead and find our y-intercept by doing something similar. Remember, the way that we find our y-intercept is we plug in 0 for x and we solve for y. Well, if I plug in 0 for x here, it's like I'm taking my thumb and I'm covering up over my x term, and then I just solve the equation that remains here. I would just divide both sides by 6, and then my y-coordinate would simply just be a point with coordinates here, 0, 6. Okay? So if all you need is 2 points to determine a line and you have standard form, very highly recommend that you go ahead and find your 2 intercepts, because that's going to give you these 2 points to plot pretty much immediately. So if I plot these points here real quick, I can go ahead and take my straight edge and line that up and get the complete picture of that line in this way. Okay? So that's pretty good. So there's my equation right there. Very quick. All right. These next couple ones here, you may need to remember a few things from a previous algebra course. So the first thing I'll do here on both of these equations is I'll just go ahead and isolate the variable. So in part C, I'll subtract 5 from both sides. On part D, I'll add 6 to both sides. And what these turn out to be are some familiar equations of lines from previous algebra classes. So part C, I get y is equal to negative 5, and part D, I get x is equal to 6. And what you may remember is this whole mnemonic device of HOY, H-O-Y, versus VUX. So that's V-U-X. Okay, so from a previous algebra class, you learned that HOY stands for horizontal lines have a 0 slope and say y equals, or in other words, they pass through the y-axis. And VUX means that vertical lines have an undefined slope and say x equals, or in other words, they pass through the x-axis. Okay, so if you remember HOY and VUX, you'll always be able to remember your horizontal and your vertical lines whenever you see them. Okay, so that is going to be something that I'll kind of throw your way as a helpful way to remember that these are basically horizontal and vertical lines here. Okay, and so if I'm trying to plot y is equal to negative 5, I'm just going to go ahead and find negative 5 there on my y-axis, and then I'm just going to go ahead and draw myself a nice horizontal line right through that point. Okay, because again, that's a HOY, so that means we've got a horizontal line through the plane just like that. All right, so very quickly done. And then also we have x is equal to positive 6, so I'll go ahead and find positive 6 on the x-axis, and then take my straight edge yet again and make sure to line that up so that it's perfectly straight, and then go right on through with my vertical line there. Okay, so very, very easily done. We just want to go ahead and make sure that that goes all the way through the grid. Looks like I missed a little bit of a part there. There we go. Draw my arrowheads, and there we are. Okay, so really, really quick to find pictures of equations of lines here sketched in the XY plane. Again, just needing to know all the little tricks and nuances there. Okay, so probably the most important part of the equation of a line is its slope. Okay, and we don't always have a nice grid to be able to interpret slope as rise over run, so given 2 points, we need more of an algebraic way to calculate our slope, and that is up here with your slope formula. Okay, so all this says is you want to take the difference of your y-coordinates and divide that by the distance of your x-coordinates. What I want you to remember here is that the order that you subtract those coordinates needs to be consistent in the numerator and denominator. Even if you wanted to go ahead and flop the order here, and instead of doing second minus first, you can do first minus second, but if you do that for the rise, you are going to have to do that for the run as well. Okay, so that's just kind of the way that slope formula works there, and I'd just like to go ahead and apply it to a couple of examples here. So in this first example here, we have the points with coordinates negative 2, 0, and 3, 1. If I calculate slope here, then that's just going to be the subtraction of my y's over the subtraction of my x's in the same order. So to avoid dealing with a negative, when I'm looking at my y's here, I see 1 and I see 0. So I might go ahead and set this up as 1 minus 0, but that forces my order for doing the x's. So that means I'm going to have to do a 3 minus negative 2, and just remember minus negative changes the operation to addition. And so this can be really easily done mentally. 1 minus 0 on the top is 1, 3 plus 2 on the bottom is 5, and so our slope for the line passing through these 2 points is simply going to be a positive 1/5. Okay, taking a look at some other examples here. So in this next one, if I apply slope formula yet again, looking at my y-coordinates, it looks like they are both 2. So as far as the order is concerned, it doesn't matter. It just would always be 2 minus 2. For the x's, though, that we have a -1 and we have a +2. I always try to set this up so that I don't have to deal with the double negative rule whenever I don't have to, because, you know, it's always an annoying rule to have to remember. So notice what happens here. In the top, I get 2 minus 2, which is 0. On the bottom, I get -1 minus 2, which is -3. And so if you take 0 divided by -3, then you get 0. And so the slope here would be 0. What that must mean is that we are dealing with a horizontal line in this example. Anytime that your slope is 0, you have a flat horizontal line. Here in this next example, we have these 2 points here, so same thing. We're just going to apply slope formula. It looks like my y-coordinates are -1 and +4. Again, setting this up so I don't have to remember the whole double negative rule there. I'll put the -1 first. So that means I'm going second minus first. So that's the order that I'll stick with whenever I do my x's here as well. So if I do -1 minus 4, I get -5. When I do 1 minus 0, I get 1. And -5 divided by +1, of course, is -5. And that is going to be my slope here. So sometimes your slope can turn out to be an integer instead of a nice fraction. Okay, but remember, if you wanted to interpret it as a rise over run, you could always rewrite it as a fraction by just simply saying -5 over 1. And then finally, for this last example here on slope, again, it looks like I just have all positive integers here, so I'll go ahead and set this up as first minus second to avoid dealing with a negative later on, and so that means I'm kind of forced to do that same thing for the x's here as well, so that would be 3 minus 3. So it looks like in the top I get 3, in the bottom I get 0, and here's where we run into trouble, because this is us saying 3 divided by 0, and we can never divide by 0, okay? So the conclusion here would be that we have an undefined slope. And that, of course, would mean that this is a vertical line, okay? So being able to kind of calculate your slope and then to interpret your slope as a rise over a run, or to interpret it as either 0 or undefined, and notice those special cases, very, very important skill for you to be able to pick up here. This next form of the equation of a line is equally as important, and this one is used most often as a tool that we can use to go ahead and find other forms of equations of lines here. And so, of course, we're talking about your point slope form. And again, it's so named because, you know, whenever we are using this form, we need the slope, and we also need a point with coordinates, right? So the point that we will use here is just whatever we're given in the problem. Here in the formula, we're just simply calling that x1 and y1. And so when you hear me recite this formula, what I typically say is y minus the y-coordinate equals the slope times x minus the x-coordinate. It turns out that this form is a direct result of slope formula that we just took a look at. We're not going to look at the derivation of that at all. But what I want you to be on the lookout for are problems where I'm giving you one of these two situations. So we're going to use this form if you either have a slope and a point of the line, or if you have just 2 points and no slope. Okay, so I want to kind of demonstrate how that's going to work with a couple of examples here. So, example 2, find the slope-intercept form. Keep in mind what form that is. That is our y equals mx plus b form. So we want to write an equation of a line in that form that passes through the point 1, -2, and has a slope of -3, and then it says graph the line. I'm actually going to go ahead and start with the graph here because I want to demonstrate these two different methods, right? If you have access to a graph, then this problem is super, super simple for the following reasons. I'm just going to go ahead and plot the point that we were given. So that's just 1, -2. That would live right here. And then I'm also given the slope, which remember that slope, if it's an integer, I can always write that over 1 to interpret that as a rise over run. And if I do that, then that might be an interpretation of for every 3 I fall, I run 1 to the right. So if I go from my point that I just plotted, I fall 3, and then I go 1 to the right, and maybe just keep that going, then I have this nice skeleton of points here, and I can use my straight edge and line this up and get a nice picture of the line pretty straightforwardly, okay? And so if I go ahead and do that here, there would be the line drawn right there. And the reason that I can get the equation pretty easily from this is because, remember, the only thing that you need for slope-intercept form, that's your y is equal to mx plus b form. All you need is the slope and the y-intercept. And those are two things that you can get immediately just by looking at the line. Matter of fact, we don't even need the line to get the slope because we were already given it. So we'll say y is equal to -3x. But then for your plus b, we just need to figure out where this line crosses the y-axis, and of course that's going to be right there at this point. And that, of course, is going to be the point with coordinates 0, +1, which means that playing the role of b is just going to be +1, and that's going to be the solution to this problem. Okay, so I want you to kind of hone in on that fact, right? If I ever give you the grid, then it's super, super easy to figure out what the equation of the line is going to be just by doing your sketch and finding your important pieces of information. But that is the problem. We don't always have a nice grid. And so what we want to be able to do is have this nice algebraic way of doing the problem. So separately, we're going to go ahead and do this algebraically, and we're going to find that we get the exact same answer. And the way that I'm going to do it algebraically is I'm going to use my point slope form. Okay? So I'm going to go ahead and just write that formula down here. And I'm going to go ahead and plug in my slope, because remember that's m, so that was -3 in this problem. And then what I want to do now is go ahead and plug in the coordinates of the point that I was given in as my x1 and my y1, okay? And so the point that I was given up here was 1, -2, so this is x1 and y1 up here. So if I come back down and I plug those in, keep in mind I would be doing y minus -2 on the left-hand side, so that's going to change to +2. And then the only thing left here is we need to do some operations and get that y completely isolated. So what I might do is I might take this -3 and distribute that in, and then after that, take it 2 and subtract it from both sides. If I do that, then what I'm going to end up with here is -3x plus 1. Okay, and that is exactly what we ended up with whenever we did the graphing method. Okay, so we should end up with the exact same answer regardless of which method we choose, but that's just a little bit of a demonstration on how to do a problem like this graphically and also how to do it vertically. Or not vertically, but graphically, I should say. Okay, in this next example, we are not given the slope, but instead we're just given simply 2 points, and I want you to remember here graphically, it's really, really easy when you have a grid, because if you just plot your 2 points real quick, which I'll just go ahead and do in the following way here, that gives me these 2 points, and so I'm just going to go ahead and take my straight edge and line that up and strike my pen all the way through. Now remember, what we need from this picture is we need the slope and we need the y-intercept. So if you are just left to your own devices and you have an access to a grid and the directions didn't say plot the line, then all you would have to do is draw enough of this line to where you see where you cross the y-axis here. And my picture isn't perfect, but what we need to drive home here is that we cross the y-axis right there, and that is going to be at a point with coordinates 0, -4. Okay? So if we have the y-intercept, remember that's playing the role of b, so b would be played by -4 here. The only other thing we would need to create the entire equation of the line is simply just the slope. And remember, that's always something that you can count out. So if I go from one point to the next, if I rise 3 and run 2, then that's going to be my slope. Okay, so m for slope is equal to 3/2. And that's all the information that I need to go ahead and make the equation of the line in slope-intercept form. Because remember, it is y is equal to mx plus b. And so if I plug in my m and I plug in my b, that would be 3/2x minus 4. And that would represent the equation of this line. Okay, so if you have the grid, it's super, super easy to create the to create the equation of a line. To do it algebraically just requires that you do a couple of additional steps, because we don't have a nice graph to look at to get the slope. That means we're going to have to find the slope algebraically by using the slope formula here. So I'll say m for slope, that is equal to, just looking at my points up there, again, to avoid dealing with a negative, I might go ahead and subtract my y-coordinates in the order of first minus second, which kind of forces the order for subtracting the y's in the denominator here. So if I were to do that, that's going to be a -1 minus 2, that's going to give you -3. If I do the run in the bottom, that's going to be 2 minus 4, that's going to give you -2. And realize here that we are taking a -3 divided by a -2. A negative divided by a negative is always going to make a positive. So I can simplify this down to 3/2, which remember, that's the exact same slope that I found in my graphing interpretation. So we know we are in good shape. It's at this point, since I have the slope now, and I have actually 2 points to choose from, I'm going to go ahead and skip straight to my point slope formula. Okay, so that's y minus the y coordinate of my point is equal to my slope times x minus the x coordinate of my point. And it is up to you which one of these 2 points you want to use. Matter of fact, since we have the graph, we can pick any other point that lies on this line that maybe crosses the grid squares nicely. The reason that I might go ahead and pick this point right here with coordinates 4 and 2 is because those are both positive numbers. And if I plug those in, then I'm not going to have to remember any of those annoying sign rules. So I'm just going to go ahead and plug in my information here using that point and using my slope. And this sets up myself nicely for being able to figure out what the equation of the line is going to be in your slope-intercept form. So if I go ahead and distribute 3 halves on the other side, I get 3 halves x minus 6. And then if I go ahead and simply add 2 to both sides, I would end up with the following answer here. I would end up with y is equal to 3/2x minus 4. And lo and behold, that is the exact same equation that we got by doing our graphing method from before. Okay, so whether you are doing this graphically or you're doing this algebraically, both methods are legit. It's just the case that we don't always have a nice grid to do our work with, so we need to be able to do this algebraically as well. Okay. Computer spazzing out on me, goodness. All right, so taking a look at this next little blurb here, we have parallel and perpendicular lines. This is something that you guys learned about in geometry class, and it also should have been something that you revisited in Algebra 2, so we're just kind of reviewing here. But the thing that you need to know is that if you have parallel lines, you need to know something about their slopes. And the thing about their slopes is that they are always going to be equal to each other if the lines are parallel. And that makes sense too, right? Like if I come up here and draw a quick set of parallel lines real quick, it makes total sense that the runs would have to be the exact same and the rises, I guess I kind of had that backwards, but you get the point. The stair patterns of these lines have to be the exact same if they're going to sit and lie parallel to each other and extend indefinitely in both directions without ever crossing, okay? So those slopes are going to have to be the exact same. For perpendicular, it's a little bit of a different relationship. Your math teacher from last year may have referred to this as negative reciprocals, but I don't really like referring to it in that way because that implies that it's always going to be negative, and that's not always the case. So I much prefer to say opposite reciprocals of each other, okay? So what is an opposite reciprocal? Well, some examples right here, right? So basically you have two slopes that are opposite signs of each other. That's what the opposite in opposite reciprocals means. One's positive while the other's negative. And reciprocals means that they are the flipped upside down versions of each other as fractions, right? So taking a look here, if one of my slopes here is a negative 4/5, then the opposite of negative, of course, is positive, and the reciprocal of 4/5 is 5/4. So those would be two slopes of some parallel lines here. 5, positive 5, and negative 1/5 would also be opposite reciprocals. Keep in mind that 5 you could write as 5/1. So if I flip that upside down, I get 1/5 and change the sign. That would make it a negative. So that would be a couple of quick examples of opposite reciprocals there, okay? Just a couple of additional notes. If you have two vertical lines, then those are always parallel. If you have two horizontal lines, those are always parallel, right? Hopefully that's obvious. And then that next line down, right? If you have a vertical line and a horizontal line in the same picture, they're always going to meet each other perfectly at 90 degrees, which is exactly what perpendicular means, by the way. Guess we should review that too, huh? Perpendicular, again, from geometry class, means you have two lines that meet at a 90-degree angle. And we are always going to make sure that we preserve that by making sure that the slopes are, again, opposite reciprocals of each other. So if I give you an example like this, number 4, it says determine whether the lines L1 and L2 passing through these pairs of points are parallel, perpendicular, or neither. That's one of the conclusions we're going to have to make is one of these three choices, then we need to know how to do that. So let's go ahead and figure that out here, right? So in order to figure out if two lines are parallel or perpendicular, we just said that we have to have this relationship between the slopes of these lines. So if that's not something that I'm handing to you, then that's something you're going to need to calculate, right? So I might come down here and do my M1 for my first slope. That'll be the slope of L1 here. And that's just going to be a straightforward application of slope formula. So pick any order you like to subtract your y-coordinates. Again, I typically like to set this up so I don't have to remember the double negative rule. But it looks like it's a little bit unavoidable here because as I move on to do my x's, it looks like I have to do a -3 minus -7, which of course changes to -3 plus 7. And so on the top I get a -3, on the bottom I get a +4. And if I have a -3 divided by a +4, that means the whole fraction turns out to be negative, and I would just say -3/4 there. All right. Moving on to my second slope, if I calculate that, again, that's me looking at the coordinates for the points in L2. Same thing, I'm going to use a slope formula there, maybe do a 6 minus 2 in the top, which means I have to do 7 minus 10 in the bottom, and that's going to give us a +4 in the top and a -3 in the bottom. So positive divided by a negative makes the whole fraction negative, and I end up with a -4/3. Okay, so the two slopes that I was able to calculate here are a -3/4 and a -4/3, and the question is, what's the relationship? Are they parallel, are they perpendicular, or are they neither? Well, the reason that they're not parallel, of course, is because they don't equal each other, right? These are not equal numbers. And they're also not perpendicular, right? You might have thought that these lines are perpendicular, but the idea is they are reciprocals of each other, but they're not opposite reciprocals of each other. You can see here that they both have the exact same sign. They're both negative. And so what that's going to mean is that these are not parallel, these are not perpendicular. This would be a case of two lines that are neither parallel nor perpendicular. If you were to graph these two lines, they would just simply intersect at an angle that is not 90 degrees. Okay, as another example here, it says, write the slope-intercept forms of the equations of the lines passing through this point. So we need to be able to pass through this point, to -1. And we also need to be parallel to this given line down here and also perpendicular to that line. Okay, so I'm going to go ahead and first point out the fact that if I give you a line that I need to either be parallel or perpendicular to, then remember, the way that we figure that out is we look at the slopes of the lines. So here I have my equation of my line written in standard form, and it's not really immediately obvious what the slope would be until I go through and I isolate this y and write it in my slope-intercept form. So I'm just going to do that really quick here. I'm going to subtract my 2x from both sides, and that's going to, of course, give me negative 3y is equal to negative 2x plus 6. And then if I go through and divide everything by a negative 3, then I get my y isolated, and y is going to look like it's going to be equal to mx plus b here. So that would be a positive 2/3 x minus 2. And again, the only reason that we did this is because we specifically needed what this slope was going to be. So playing the role of m in my slope-intercept form here turned out to be a 2/3, okay? So just keep in mind, if I want to be parallel to this line here, so I'll just do the parallel symbol there, just the double bar symbol. If I want to be parallel to this line, then I have to keep the same slope. I have to be equal slopes to it. Keep it 2/3. However, if I want to be perpendicular, do the perpendicular symbol there, to that line, then I need to use the opposite reciprocal of a positive 2/3, which the opposite of positive, of course, is negative, and the reciprocal of 2/3, of course, is a 3/2. Okay? So depending on what kind of line I'm trying to construct, I'm going to need to use these slopes accordingly. Well, in part A, I need to be parallel to this line and pass through that point to negative 1 here. So let's go ahead and set that up, right? So in part A, if I want to be parallel, then that means I'm going to have to use the parallel slope, which is going to be 2/3, and I want to, of course, pass through the point to negative 1 here. Okay? Well, how could I possibly find the equation with this slope and this point? You guessed it, I'm going to go back to my classic point-slope formula because that's the information that I have. So y minus the y coordinate, that would be y minus negative 1, which changes to y plus 1, is equal to your slope, which we found to be 2/3, times x minus the x coordinate. So there's the setup for the problem right there, and now there's nothing to it but just go through and distribute on the right-hand side. So that's going to give you 2/3 x minus 4/3. That is equal to y plus 1 on the left-hand side. And then finally, we're just going to go ahead and bring that 1 over by subtracting. And we're going to get y is equal to 2/3 x. And then this 1 right here, I can go ahead and rewrite that 1 as a 3/3, so it has a common denominator with the fraction that I'm trying to subtract from. And so if I have negative 4 minus 3, that's going to give me negative 7, of course, and then over 3. Okay, and so there is going to be the equation of the line that passes through the point that I wanted. That's going to be parallel to the equation that I was given. Okay, but keep in mind in part B, we also have to do the case where we want to be perpendicular to that line and pass through that point. So let's set that up for ourselves now. So if I want to be perpendicular to that line, then I have to use the perpendicular slope, which we already calculated. That's going to be a negative 3/2. And I still want to go ahead and pass through that point with coordinates to negative 1. And so again, I'm going to set that up using my point slope formula. And so again, y minus negative 1 changes to y plus 1. And now the only change is that I'm going to go ahead and plug in the slope that it would take to be perpendicular instead of the slope that it would take to be parallel. So here I'm plugging in a negative 3/2, and that's going to be multiplied times x minus 2. And there's my setup. I'm just going to go ahead and distribute on the right-hand side. So I'm going to end up here with negative 3/2 x plus 3. And that is equal to y plus 1. And just like last time, I'm going to bring that 1 over now. And we're going to end up here with y is equal to negative 3/2 x plus 2 as my final answer for the equation of a line that passes through that point to negative 1 and is perpendicular to the line that I was given. Okay, so just to summarize there, if I give you the equation of the line written in standard form, you're going to have to isolate y to get it to look like your slope-intercept, your y equals mx plus b form. And then we're going to pick out the slope. We're going to figure out what it would take to be parallel or perpendicular by changing those slopes accordingly, and then use point-slope formula to get our final answer. Here in example 6, it says find the slope-intercept form of the lines passing through 4, negative 2. That's parallel and perpendicular to this line. Okay, so I'm going to do this example in a different way here because the last example is very, very similar to this one. However, you might notice that what I just gave you here is a horizontal line. So the algebraic method has its uses whenever possible, but if you have a horizontal line here, this is something that is super, super easy to create a quick sketch of. And so that's how I'm going to go ahead and do this problem, is just simply by creating a quick sketch and then just kind of applying my spatial reasoning to solve the problem here. So there's the x and the y axes, here's 0. If the equation of my line reads y is equal to 1, remember that's a horizontal line, that's a HOI, right? So I'm going to go ahead and find positive 1 on the y-axis, which let's say is just simply right here. And then I would just simply go ahead and take my straight edge and then line it up at negative 1, or not negative 1, positive 1. And then I would just simply go ahead and make my straight line just like that, okay? So there is the equation of the line y is equal to 1, okay? Now, read the question back again, right? We want to be able to pass through the point 4, -2. So on my sketch here, I'm going to go back to my origin point, and I'm going to go ahead and navigate to the point with coordinates 4, -2. So that would just simply be to go 1, 2, 3, 4 units to the right, and then go down 1, 2, and that would put me approximately about right here, okay? So let me go ahead and fix my picture so it looks a little bit cleaner there, right? So just go ahead and erase that real fast, and just clean this up a little bit so I extend a little bit further, and I'll fix my point here even too. Okay, there we go. Okay, so this is going to be the point with coordinates 4, -2, okay? Now, if you read the question again, we want to be able to pass through that point, and in part A, I want to be parallel to that line, and in part B, I want to be perpendicular to that line. So if I want to be parallel to this line and pass through this point, then all that's going to take is that I line up my straight edge here. Okay, if I want to be parallel to it, then I'm going to go ahead and keep my straight edge perfectly flat like this, but I'm going to go ahead and go down here so that I'm passing through that point. And again, my sketch is not perfect here, but if I go ahead and strike through that, the way that I got down there, I guess, if I fix my picture here a little bit, the way that I got down there is I went down 2 units. So I know that that's going to cross the y-axis at -2, which means that this is going to be the line with the equation y is equal to -2, and that is actually your answer for part A right there, okay? So the line that is parallel to the line that you were given, that passes through the point that you were given, is also going to be a horizontal line, and that's going to be a line with the equation y is equal to -2. But keep in mind, we also want to be perpendicular, so if I take my straight edge and I now go perpendicular to the line that I was given, and also passing through that point, then I might be a line that looks exactly like this. Okay, just goes straight up and down there for us. And again, that is going to always be perfectly 90 degrees, meaning that we are indeed perpendicular. And what is the equation of that line? Well, again, I have to fix my drawing here because it's not exactly perfect. But remember, the way that we kind of got this point down here is we went over 4 units. So that must cross the x-axis at 4. And so that must mean that the equation of this line is going to be a vux. Remember, x is equal to +4, and that represents our answer for part B there. Okay, so again, the algebraic method has its uses whenever we, have lines that are not so easy to draw as these horizontal and vertical lines. But if you create a quick sketch and use some geometry, these are going to actually be really, really easy problems for you to do. So keep on the lookout for any of those hoys or any of those vuxes. Okay, it would be the exact same here in example 7. I'm going to go ahead and skip this for the sake of time in the video. If you want to check out the complete example 7, then I would say check the content library for the complete set of the notes. But here's just a quick slide to summarize all the things that we talked about here in this video, and then the assignment to follow thereafter that. So I hope that this video has been of some help to you. Hopefully you've had some some of these things are starting to kind of come back to you here. So remember, if you have any questions whatsoever, always feel free to ask those questions. I'm always happy to answer whatever questions you have. But that's going to do it for this video. Thank you very much for your attention, and I will speak to you in the next one.